All right, so we are to our specialty reagents again. And based on our starting material in our product, you can see what happened here. We have alcohol over here and the chlorine over there. So somehow this thionyl chloride, SOCl2, must have substituted a chlorine for that OH. And again, I think it's a lot easier to kind of think through mechanisms to remind us of how reagents work instead of just trying to memorize them. It's easy to confuse things when you're just doing it by the memorization way. So thinking about the whole negative flows to positive thing, what would the first step of this reaction be? This is going to be our negative, so what's most electropositive over here? So what is the greatest partial positive? Chlorine, sulfur, or oxygen? Again, you'd go to your periodic table for this. You've done it. Good job. Sulfur is the most electron poor, so the oxygen is going to add to that sulfur, and that's going to lead to the chlorine going away. And that would provide us with this intermediate here with the O now bonded to the sulfur. And we have our positive charge there. At this point, we have one equivalent of pyridine. When we were using POCl3, we were using excess pyridine. With one equivalent of pyridine, that pyridine is going to act as a base. It's going to deprotonate that alcohol. And that would leave us with that species there. And essentially the ammonium salt of that nitrogen. So it would be NH with all those bonds, meaning it has 4 bonds to it, so it's going to be positively charged. At this point, the only other thing we have around is this chlorine that left, Cl-. And this is a good leaving group. It turns out that when it leaves, it's forming this thing SO2. And now I want to kind of bring your attention to this bottom statement on the course packet. The product is a single molecule, so I don't have anything wavy up here. That must mean that the reaction proceeds via a blank type mechanism. What would belong down there? If it was a unimolecular type mechanism, that would mean that we were going through a carbocation, and that would mean that the nucleophile could add to either side, right? But here, we only get one product molecule, and it's inverted. So what that must mean is that it's going through an SN2 or a bimolecular type mechanism. So we have our leaving group, we have the Cl-, it has to add to the back face of that OSOCl leaving group. So that would add there. This guy would go like that. It's going to form an OS double bond. SO2 looks like this. So that's how it gets the other double bond, and then this Cl will leave as Cl-. So technically, we have our substitution product. That's what we really care about. Again, we really only care about the organic product. If this was a predictive product and you didn't write any of this other stuff besides that, that would be okay. What else do we have? We have Cl-, and that's from that right there leaving. And we also have this pyridine molecule that was protonated. So these are salts formed together. Remember, salts are ionic kind of things bonded. So this would be kind of an ionic bond between that positive and the negative. So this is a specialty reagent. Again, I mentioned specialty reagents. They always do bimolecular things. So when you see something like SOCl2, POCl3, it's kind of hard to reason out why one of them does elimination, one of them does substitution. That is something that I think you're going to kind of have to memorize. But working through the mechanisms, writing those things out, at least help you build those memorization kind of connections a little bit better. And hopefully some of the arrows are intuitive. I'd say this first arrow is very intuitive, negative flowing to positive. This is an acid-base reaction, that's intuitive. But why this chlorine does a substitution instead of an elimination at that step, that's kind of something that's not very easily explained. And we would have to go very much more in depth to kind of get at something like that in this course. So there are things in organic chemistry, not a lot of things. I would say most things you should be able to reason out instead of memorize, but this is something that like SOCl2 versus POCl3. POCl3 does E2. This one does SN2. That's something that is more memorization based. So more on that in a minute. All right, more on SOCl2. Why do we even care about it? Why is it useful? Well, how else would we substitute an alcohol with a chloride? The only other way we have to do that is HCl. So that's what we just talked about a moment ago with substitution reactions. HX, the X substitute for the alcohol. So if we wanted to do that, we would have to use HCl. But we see what thionyl chloride does with that. It makes that. What would HCl make if we mixed it with that same cyclohexane alcohol molecule? So this is a good time to go over that. Predict the product here. What is going to happen? So do that right now. Pause it. Come back. Great job. You did it. Okay, so what's going to happen here with HCl? Well, we're going to get our good leaving group to form. And at this point, we have Cl-, but Cl- is not a very strong nucleophile, and this is a really good leaving group. It really wants to leave, and it's going to do that without the chlorine being involved. So it's going to leave. It's going to make this secondary carbocation, and then what's going to happen next, guys? If we have a secondary carbocation, we could have a more stable carbocation potentially. Is there a more stable position, one carbon away? Why, yes, there is. Right here, we have this hydrogen on a tertiary carbon that could jump on over. That would mean that we then had a tertiary carbocation, and the Cl- will ultimately end up adding to that. Again, do we have to have a wavy bond here? No, because this is, again, not a stereocenter in the product. This side of the group and that side are the same, so this is not a stereocenter, so we wouldn't put a wavy bond there. Again, we only put wavy bonds if there are two molecules represented by the structure. So back to the beginning question. Why is SOCl2 useful? Why is thionyl chloride useful? Because if we want to make that, we can't use HCl. We would have to do some other method because rearrangements are occurring. So back to the course packet, if HCl was used, an unwanted carbocation rearrangement would occur that would prevent us from getting the desired product. Okay, one more specialty reagent right now. All right, so specialty reagents, we mix them with a species, and in that one reaction, they produce a product. That's kind of how I'm defining specialty reagents in this chapter. And the next one is called PBr3. And essentially, there is a mechanism in the textbook. I'm not too concerned that you know the mechanism. What I want you to do is think about it as the same thing as SOCl2. It's just Br instead of Cl. So SOCl2 did an SN2 reaction. That's a Cl right there. SOCl2 did a Cl, substituted an alcohol for a Cl. PBr3 is going to substitute a Br for an OH. How did SOCl2 do it? By an SN2 reaction. How's PBr3 going to do it? By an SN2 type reaction. So this alcohol will do it by an SN2 type mechanism. It's not going to have time to rearrange. So that would mean the alcohol is on the front face, so the Br- adds to the back side. So again, just another specialty reagent. They'll talk about it a lot, or they'll use it in future chapters, so we definitely have to know both of them. And on the course packet, again, I have another bullet point. It says SOCl2 and PBr3 work by SN2 type mechanisms. Therefore, they do not work well with blank alcohols because of blank. So this is a secondary alcohol, should work fine there. Primary alcohols also work fine, but how did SN2 work with tertiary leaving groups? Not well, right? Tertiary leaving groups were so crowded that nucleophiles had a really hard time reaching that antibonding orbital. So that's essentially what we have to add here. SOCl2 and PBr3 work via SN2 type mechanisms. Therefore, they do not work well with tertiary alcohols because of steric hindrance. So there is a tertiary alcohol right there. PBr3 or SOCl2 would give no reaction with that. The last thing on this page is just a summary of the reagents and stuff for the alcohol substitution reactions, straight out of your textbook. So if you don't have this packet, you can look there. Woohoo!